Fundamental types of crystalline solids. We've got crystalline solids can be divided into three broad categories based on what are the particles in those solids. So we can have a molecular solid where we have individual molecules forming the solid. We can have ionic solids where we have ions forming the solid, and we can have atomic solids. Atomic solids, the composite units are atoms. We can divide those atomic solids into three other categories: non-bonding, metallic, and network covalent. And the difference here is what's holding those atoms together. Non-bonding, those atoms are just held together by dispersion forces. Those are the only intermolecular forces that atoms have, is the dispersion forces. A metallic atomic solid has atoms in it, but they're held together by metallic bonds. So we've got the electron C that's around the atoms and it's holding them together. A network covalent solid has atoms that are covalently bonded to each other throughout the entire crystal lattice. And so a diamond is an example of this. Quartz, which is silicon dioxide, another example of this. A piece of quartz is truly one ginormous molecule. There's no intermolecular forces. The silicon and the oxygen in it are covalently bonded to each other all the way throughout. So these slides give a little more detail. Molecular solids, the composite units are molecules. The molecules are held together by whatever intermolecular forces they have. The strength of those intermolecular forces is going to affect their boiling points and melting points. In general, though, molecular solids tend to have fairly low melting points because intermolecular forces are not that strong. So solid water, dry ice, those are molecular solids. You can have different forms of a molecular solid that has the same chemical composition. These are called polymorphs. Poly is a prefix meaning many. Morph refers to shape. So these polymorphs can have different physical properties, including melting points and solubilities. And it depends on how the molecules are arranged. An example from your textbook is crystalline forms of cocoa butter, which is the yummy part of chocolate. There's actually 6 different crystalline forms. Making chocolate is very much an art. We've had some fiddly experiments in lab. This is even more fiddly. You have to get it just to the right temperature at the right rate, and sometimes you need to heat it up and then let it cool down just right so that you get the correct polymorph. If you've got poor quality chocolate, you may notice that it's got bloom on it. It kind of looks like moldy bread, but it's not mold. It's just what happens with many of the polymorphs of chocolate. And it's not harmful, it's just not very pretty. Good chocolate should have this nice shiny surface and not get bloom on it. So you can read about that in your textbook. Ionic solids, the composite units are ions. Those are held together by ionic bonds. Ionic bonds are pretty strong. And so these generally have very high melting points. We're going to talk about ionic solids in way more detail later. So more on that. Atomic solids, we've got the composite units being atoms. So solid xenon, solid iron, solid silicon dioxide. Now, SiO2, that looks like a molecule, doesn't it? But silicon dioxide is not a molecular solid because in a molecular solid you have discrete molecules held together by intermolecular forces. In silicon dioxide, which we call quartz, the silicon atoms and the oxygen atoms are bonded together with covalent bonds. There are not individual discrete molecules, so it doesn't constitute a molecular solid. Non-bonding, just held together by weak dispersion forces. They're going to form whatever closest packed structure will maximize their coordination number or minimize the distance. They have very low melting points because the molar dispersion forces are so weak. Those melting points will increase with size, with molar mass. The only examples of non-bonding atomic solids are noble gases in their solid forms. And you just have to cool them way, way down, and you can get them to solidify. Metallic atomic solids, you've got metal atoms. So the metal atoms, remember, send an electron or two out to play in the neighborhood, and these guys swimming around is what holds all these different metal ions together. They're also going to form closest packed structures. The bonds are non-directional, so they can just nestle together however they wish, and generally that's going to be a closest packed structure. The melting points of metals vary depending on how strong those metallic bonds are. Mercury is a liquid at room temperature. The bonds between the mercury atoms are weak. Other metals melt at very, very high temperatures, and so it's kind of all over the place. Network covalent solids. Here, the atoms are held together by covalent bonds. Diamond, graphite, silicon dioxide, these are all network covalent solids. Here, we do not have closest packed structures forming because it's not just spheres falling together like balls. There are covalent bonds. Covalent bonds have geometries of how the orbitals overlap. And so the structure is limited by the geometry of the bonds that are formed. Network covalent solids tend to have very high melting points because covalent bonds are very strong, holding them together. So we should be able to answer questions like this. What type of atomic solid is gold? So atomic solid, what are the three kinds? Non-bonding, metallic, and network covalent, right? What kind of an element is gold? It's a metal. So it's a metallic atomic solid. I put questions like this on the exam, hoping that they're, low-hanging fruit, right? And then people have, they overthink them and they mess it up. So if it didn't say atomic solid, you look at this and it's AU. That's not a molecule, right? Those aren't ions or anything. So it's an element. It's most likely going to be an atomic solid. It's a metal, so it's a metallic atomic solid. We should be able to predict boiling points or melting points. So here we've got three compounds, and they're asking which solid would you expect to have the highest melting point? What makes for a high melting point? The particles being held together strongly, right? So for highest melting point, we're looking at which of these has the individual particles held together by the strongest forces. So what forces are holding magnesium and oxygen together as a solid? Ionic bonds, right? This is an ionic solid. So let's just write that down. It's an ionic solid, held together by ionic bonds. What about I2, solid iodine? Is that an atom? Is it ions? Is it a molecule? It's a molecule, right? I2. So this is a molecular solid. What are molecular solids held together by? Intermolecular forces? What about krypton, solid krypton? It's not kryptonite, that's what Superman has an issue with. Is krypton a metal? Find it on the periodic table. No, it's a noble gas. So it's not metallic bonding. It's not a metallic solid. Is krypton likely to form covalent bonds with other krypton atoms, being a noble gas? No. This is one of those non-bonding atomic solids. So it's held together by dispersion forces. dispense. That's an R. Whoops. Dispersion forces. So we're looking at these three solids and identifying what's holding them together. So MgO is held together by ionic bonds. I2 is held together by intermolecular forces, which would be what for that one? I2. Does it have hydrogen bonding? It doesn't have hydrogen in it, and it can't possibly. How about dipole forces? Is I2 polar or nonpolar? It's nonpolar. Two iodine atoms bonded together. That bond has to be nonpolar because it's two identical atoms. This is nonpolar, so this is also held together by dispersion forces. So we've got ionic bonds, dispersion forces, and dispersion forces. Which one's strongest? A. Ionic bonds are strongest, and so magnesium oxide is going to have a higher melting point because those ions are held together by much stronger forces. Now, you could go down here and argue about which of these is lower, but the question doesn't ask us to do that. You'd have to do that based on molar mass, and it would be approximate. Any questions? So, the network covalent atomic solids, there are relatively few examples of those. There's silicon dioxide, which is quartz. It's the main ingredient in sand and in glass. Graphite and diamond and some of the other forms of that, like graphene and buckyballs, those are just carbon. Carbon likes to form 4 bonds with other carbon atoms, and so any form of carbon is likely to be a network covalent atomic solid. Any of the other ones, I would expect you to just look, is it an atom, is it a molecule, and say molecular or atomic based on that. Any questions?